Hi, today we're working on a problem where we look at the relationship between molecules and moles, or really for that matter, any other type of particles related to moles. And when we do this, we're counting at an atomic level or we're counting in quantities of moles. So something to keep in mind, anytime we talk about particles, we also can use the same relationship we're going to see here for atoms or ions or formula units or molecules. And the relationship, or the unit conversion, that relates these particles to a mole is Avogadro's number. And that's going to be 6.022 times 10 to the 23rd, whatever kind of particles, per 1 mole of that type of particles. Okay, so anytime we need to go between particle and mole, we're going to use Avogadro's number in yellow here. So let's move to our problem. And I've got down in the corner a reminder that when we solve these problems, we want to look at the given, the goal, establish the relationships, set it up, answer it, and then don't forget to check it. So let's read the problem here. How many molecules are there in 1.32 moles of SO2? Okay, I always want to start by writing that given down, 1.32 moles of SO2, and don't forget to put your chemical formula with your numbers here, and then my goal is going to be to get to those molecules. Once I have my given down and my goal down, that helps me start to think about what type of relationship I might find between molecules and moles. So I think molecules, that was one of my particles, and moles, I can relate those two directly using Avogadro's number. So, just like before with unit conversions, I let the units be my guide. If I have moles in the numerator here, I'm going to put moles in the denominator so that they'll cancel out. 1 mole of SO2 is equal to 6.022 times 10 to the 23rd molecules of SO2, and now if I calculate that, I get 7.95 times 10 to the 23rd molecules of SO2. Remember, I'm going to multiply in these unit conversions through all of the numerators and then divide by the denominator, which is easy in this case because it's a 1. I want to check the significant figures. I kept 3 significant figures to match the 3 significant figures in the given here. And then do a final check. If you're counting to find molecules, then you should have a lot of them. In other words, a large exponent at the end. And so that checks out here. And punch all those numbers through your calculator one more time as well for a check. Now, one more quick thing that you might be asked to do here is go from the molecules of SO2 to the atoms of sulfur or the atoms of oxygen. So let's go to a clean page and look at that real quick here. So if we look at what we've got here, we've got that number that we found on the previous page that we had, 7.95 times 10 to the 23rd molecules of SO2. If you were asked to find the number of S atoms over here, then I need to look at the structure here, or the count of the atoms in a sulfur dioxide molecule. And I see that for every 1 molecule of SO2, there is only 1 S atom. So I can easily follow that correlation of one of these to 1 S atom to say that if I have 7.95 times 10 to the 23rd molecules, I'm going to also have 7.95 times 10 to the 23rd S atoms, a 1-to-1 ratio of the molecule to the atoms. And if I continue that to look at oxygen atoms down here, I say, all right, for every 1 molecule of SO2, I have 2 O atoms, these 2 right here. So that means I need to double the molecules to find the atoms here. So if I take 7.95 times 10 to the 23rd molecules and double that, I come up with 1.59 times 10 to the 24th O atoms. And so now I've gone from molecules to sulfur atoms or molecules to oxygen atoms. Hopefully that helps you out today. Thanks for listening.